All right, ladies and gentlemen, what we're going to do here is we're going to talk about the law of conservation of momentum and most of the things that might be mentioned on your AP test. Now, this isn't everything. This is giving an ongoing list, but this is the first part in that series. So the law of conservation of momentum very briefly goes in one quick direction, and that is just how do you calculate momentum? And that is this momentum value here, which is this Greek letter rho, equals mass times velocity. Now, since velocity is a vector, momentum is also going to be a vector. And so the direction here does matter. And what you usually denote as positive momentum is to the right or up, and negative momentum is to the left or down. For this, the units of momentum are kilogram meters per second. The next part is when you look at what is exactly is a change in momentum, and that's going to be denoted as mass times your change in velocity. Now, this is considered impulse. Impulse can be calculated one of two directions. It could be looking at the change of velocity of an object, or the second formula for it could be, which is going to be force times your change in time. Now, for this delta t interval, so delta t usually is a small number, like very, very small, like with less of a second. Force still being in the units of newtons. And so what you get in here is a unit of impulse can be calculated one of two ways. Impulse can be either, which would be still be kilogram meters per second if you calculate it using this method up here, or it could be calculated on saying Newton seconds. Now, what you typically don't say is you don't say the momentum of an object is Newton seconds. You usually say, if you're using this Newton seconds, you're talking about just the change in momentum or just impulse only. Every once in a while, depending on what sources you look at, you'll also find this delta P written as a J. I typically don't tend to use that because people tend to get energy and that J for impulse mixed up. Alrighty, so we're done going in that direction. And so the next thing we're going to do is we're going to change gears a little bit, and we're going to talk about collisions. Now, when you talk about collisions, you look at momentum of an object, where momentum before equals momentum afterwards. Now, in this class, this is always going to be true as far as AP Physics 1 goes. If you ever take any further physics courses, they may talk about how that is not always the case, but in this class we're going to say momentum is always conserved. So the momentum before a collision is going to equal to the momentum after the collision. Now, the first type of collisions we have is going to be what we're going to call elastic collisions. Now, elastic collisions, so beforehand, what you tend to have is one object is going to collide into a second object, and then afterwards, all that momentum is then usually transferred into that second object. Now, what we see here is this first object had momentum, hit the second object, and then afterwards, the second object's then flying away. Now, what if both objects then had momentums going towards each other? So before, you could say this object is going to the right, this object's going to the left. What are they going to do after the collision? And they're going to bounce off of one another. And what you're going to notice is that their velocities swap. So we notice here the velocity here is 0. That means the velocity here is going to be 0. And whatever these velocity vectors are, they're usually going to swap as well. Now, with elastic collisions, what you have to say then is that what you notice is that the kinetic energy of the system is also conserved. So usually if the question asks if the collision exists, first thing you check is momentum conserved? And then if momentum is conserved, you find if kinetic energy is conserved. If those two are true, then you find out then your object is having an elastic collision. Going to the next gear, which would be considered an inelastic collision. Now these can be a little interesting, where beforehand, if we have one object going into a second object that's not moving at all, afterwards what you notice is that the objects don't necessarily switch velocities, and this second object tends to be going a smaller value. So things still happen and we can predict those velocities, but something in here was lost. Now if we do the same situation here, if we were to calculate the kinetic energy in the system, you would find out that the kinetic energy initial is not going to equal your kinetic energy final. And the reason that is that work was done on the system. So this means when those two things hit, there's usually sound energy that was lost, or there was some heat due to friction, etc., etc. What we can say is that the energy of the system was not conserved. Now, the last one that we talk about is perfectly inelastic collisions. So perfectly inelastic collisions are when things hit and stick. So beforehand, if this object is going to the right and this object is standing still, what we then notice is then afterwards both objects are then going to the right, but not near as fast as you originally were. And if we were to have the same situation where beforehand both objects are going towards each other, we notice that after the collision their momentums cancel out, and this causes their velocities to be zero. Here we can also find out that kinetic energy is not conserved. So it's really easy if things hit and stick to understand how kinetic energy is not conserved, but what you can't do is if things bounce off one another, you can't assume that's an elastic collision. You then might have to do a little bit more work of looking at their energies to determine if energy is conserved or mechanical energy is conserved, it's elastic collision. If mechanical energy is not conserved, then it's inelastic. Okay? Now, this is a lot of stuff just conceptually, but here, what does this look like mathematically? So what I'm going to do is I'm going to work on this, and I'm going to downsize it just a little bit. Let's see if I can get this not to rotate, but to downsize for me. Let's try it again. There we go. And so what I'm going to do is move this off to the side. So now we're going to talk about the next layer, which would be how to use this stuff mathematically. And the first thing that almost in any collision system I ask myself, was there an outside non-conservative force? If not, then you have to say momentum before equals momentum afterwards. Now here, at this point, I want you to ask yourself, how many objects are present? So let's do the example here of, let's say that one object is colliding with another object, and then after the collision, both of them stick together and are still going to the right. So the first thing we ask ourselves is how many objects are present? And what here we'd say is before this collision, we see two objects are present. So I'd say the momentum of the first sphere plus the momentum of the second sphere would be equal to the one object in total. So we'll call that momentum final total. And from there we can break this down. We could say mass 1, velocity 1 plus mass 2, velocity 2 equals mass total, velocity final. Now you might be asking yourself the question is, okay, how do we simplify from here? Well, usually we note that if an object's not moving, its velocity is 0. So from there we can say that this whole system right here is going to cancel out. And what you find is that your velocity, so mass 1, velocity 1, we could say mass 1, velocity 1 equals mass total, velocity final. That would be an example of using the momentum, law of conservation of momentum with collisions. Doesn't really whichever you do, it's just as long as you stay with that question of how many objects are present. You can say before the collision and after the collision. You can expand your formula out and then continue forward. Now, what if my objects, instead of sticking together, I had, let's do another example, and let's look at if these objects were bouncing off of one another. So what I would do here then is, I'm going to clean up this space a little bit, is I would then say, let's do if two spheres are going to collide with each other, and then they bounce off. What would then this look like mathematically using the law of conservation of momentum? That's momentum before equals momentum afterwards. We would say mass 1, velocity 1 plus mass 2, velocity 2 equals mass 1, velocity 1 final plus mass 2, velocity 2 final. Okay, now there's a couple things that we need to denote in here, is that the velocities of my objects beforehand, this is denoted as a positive velocity, so that means the momentum here is also going to be positive. Same thing over here, as we know that this momentum is denoted as positive. So we can see here that the momentums actually were switched. And then up here, we see that this velocity is negative, and that this velocity is negative, and that in this elastic collision, because things bounced off, and we're going to call that the velocities were swapped, we can see that their momentums were flip-flopped. Okay? Now, the last example would be if things were initially together at 0. And so what I'm going to do is I'm going to clear this off, add another layer, and let's do if my objects were starting at 0. So let's do one object before the collision, and then afterwards half of my sphere, let's call this an explosion, goes to the left, the other half goes to the right. And let's call this first piece over here, let's call the whole thing mass of 3m. Let's say this is 2m, and this is just a mass of m. Predict the velocities of each individual piece. Well, the first thing we notice is that the object beforehand is not moving. So momentum beforehand is going to be mass times a velocity, where my velocity is 0. And then we're going to call the piece, let's call this total. The piece going left we'll call mass 1. So this is going to be mass times velocity 1 plus mass times velocity 2. Now my mass here is going to be 2m. Now the first thing that we're going to notice here is that when this velocity, since this one off the left is negative, what you get then is 0 equals negative mv1 plus 2mv2. And that's because these two need to cancel out to each other to come to 0. So I'm going to say then that is that the magnitude of the piece going to the right is going to be equal to the magnitude of the piece going to the left. And then mass here is going to cancel out. And so we can then see that velocity of 2 is going to be 1/2 of the velocity of 1. Meaning, or that the velocity is going to be half of the velocity 1, so that this piece, let's say if this piece to the left was flying off at 10 meters per second, this piece to the right is going to be flying off at 5 meters per second. And that's because since this piece has less mass, this piece has more mass, it's going to be flying away with less speed. Alrighty folks, I'm going to wrap it up right there, and we're going to call that the first part of this video is complete.